Here we want to just know our concavity structure and our inflection point. So that means we need to deal with our second derivative. So to find our second derivative, we need to first of all find our first derivative. You could write your original function as just 6 times your denominator to the negative first power. Then all you really have to do is just do your power rule with the chain rule. You could use a product rule here, or you could use a quotient rule on the original, but it's easier this way. We end up then with our first derivative being a negative 12x over your denominator squared. At this point, I would say go ahead and use your quotient rule. So we're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom. You put your exponent in front, decrease your exponent by 1. The 2x comes from the derivative of the inside, all over the bottom squared. You'll notice that you have a 2x plus 3 here. You could drop that out, drop one of these out with one of these on the bottom. And so then you end up with a 36x squared minus a 36 on top, which you could pull out that 36. Your critical points then are going to be where your derivative is undefined or 0. The bottom is never going to be 0, so it's never going to be undefined, because when you square something, it's greater than or equal to 0. Add 3, it's greater than or equal to 3. And cube it, it's always going to be greater than or equal to 3. So the bottom's never 0. Set the top equal to 0, and that's when you would get plus or minus 1 for your critical points. So then we want to go ahead and put that on a number line. Our negative 1, our positive 1. Then you want to check a number in each region into your second derivative. Try a number over here, negative 2. You know the bottom's always going to be positive. Put a negative 2 here, we get a positive, so we know we're concave up. Try a number in between, say 0, so that gives us a negative on top. The bottom is positive, so we get a negative. Try a number on the far right. Put, say, a positive 2 in, we get a positive on the top, positive in the bottom, so that means we're going to be concave up again. So we're switching from concave up to concave down, so we have an inflection point. Concave down to concave up, another inflection point. Once again, to figure out those y coordinates, you need to go ahead and plug 1 and negative 1 into your original function. Plug 1 in here. You're going to get 6 over 4, or 3 halves. And you're going to get the same thing when you plug in negative 1. So where is it concave down? From negative 1 to positive 1. Where is it concave up? From negative infinity to negative 1. And then from 1 to positive infinity. So you know over here you got to be doing some concave up, then you got to be doing some concave down, and then you got to be doing some concave up. You should remember that since we're dealing with a rational function like this, there's a higher power in the bottom than there is at the top, that it's going to be a horizontal asymptote of y equals 0. So when you go far to the right, it's going to level out at a height of 0. Far to the left, level out at a height of 0. And here you're going to come in, you're going to be concave up to here, then you're going to be that concave down, and then as you leave again, you're going to be concave up.